Let's now see how this data preparation is done practically. Before that, we import TensorFlow, we import text vectorization, which will help us a great deal in preparing our data. We import NumPy, we import RE, that's for regex tasks. We import string for manipulating strings. We import NLTK for certain NLP tasks, or basically for manipulating the different input texts. Now for data preparation, we have the directories. So this is where our data is found in our computer. And note that we had seen this already, where we have this supervised, which is the training set, and then the test for our validation. So we've considered that we have the training and the validation directories. And in these two directories, that's for this train directory, we have two subdirectories, one for the good reviews, one for the bad, and this other one, two subdirectories, one for the good reviews and one for the bad. And then next, we make use of TF the keras, the preprocessing the text dataset from directory to actually collect this data which is found in this selected directories, and then convert them into a form which can easily be processed by TensorFlow. So we could simply from here do from, copy this, put this right here, that's TensorFlow. We import text dataset from directory. So that's it. Then we run this, we've run this, and then run this. We have here found 25,000 files belonging to two classes, which actually coincides exactly with what we had seen previously. Now the next thing to do will be to replicate same for the validation data. We have val dataset, here val directory. So basically we run this again, and we could take off this batch data size. So we have this. Now we have the two, that's the train data set and then the validation data set. So from here we could actually see exactly what these data sets are made of. Now in order to see this practically, we have the val, or say the train data set, the taking one value, we have the review and then the label. Let's now get the values. We have for review label. In this we print the review out, so we print the review, and then we print the label. So run this. Notice that we have 8 different reviews with 8 labels, since that's our batch set size, our batch size. So let's take this to 1, run it again, run this. So we could just have one review to look at. Now we have this one review. We have psychotic transsexual Bobby murders the patient and all of this, and it ends with a 1. This tells us that this is actually a positive review. Now since the shuffle is true, we could run this again. We have a different, so we have this different ones, and we could look at this. This film isn't just about a school shooting. In fact, it's never even seen, but that just adds to the power this film has. So clearly we could see here that this is a positive review and ends up with this 1. Let's check for our negative review. Run this again. And then finally we fall on this negative review, which is seen clearly here with this 0 label. So basically this is our data set, and from here we're going to process this input sentences before sending into our model. Let's get back to a batch size of 8, as this is what we're going to be using for training. From this, we now see how to standardize our input sentences. So we could define this function, process sentences, which basically does that processing. The aim of this function is basically to pre-process the sentences, or standardize the sentences, and then we have as input basically the sentences. Let's say the raw reviews, and then we have now the standardized reviews. So let's take a look at that. Now, in order to lower, that's to convert all our input sentences into lowercase, we have TensorFlow.strings.lower, which does the job. So if you have this input, let's comment this other portions. We have this, and then we have this pre-process sentences of an input. Now let's come and just collect randomly some input from here. Let's take this right from here, and then we could end here. So we have this, copy this, then let's create our input here, input data, which is this. We have that. We could actually make this shorter, so let's just do this. Take this off. Anyway, there we go. So we have this input data which we've been given, and then we have this pre-processing. Run this and see the output. So pre-process requires the input data, so obviously we'll just put this input data inside here, run this, and there we go. We have now our input, which came with this I. See, it turns into the small I, this turns into this, and then we could also do something like this. We have upper, run it, we see that everything is converted to uppercase. So to convert everything to lowercase, we simply do this. So that's the first pre-processing step we have for the sentences. For the next, we are going to remove the HTML tags. To do this, we're going to use the regex, which comes with strings, or the TensorFlow.strings package. So let's do this and comment the section. Then we run it. We have this new output. We see here that we don't have this HTML tags as we had previously. Now this has been taken off. And how does this work? Simply using the regex principles, we start with this. So once we have this less than sign, as we could have in the HTML tags, it has been matched up with every portion of the sentence which has this less than sign, and then we negate the greater than to say that if we have, for example, let's take an example where we have this, for example. So we have this greater than which follows. We'll run this and see the kind of output we have. We see that in this case, this is not taken off, or this first HTML tag is not taken off, as we could see clearly here, whereas this one is taken off. And this is simply because we're supposing that if we have the less than followed by the greater than sign, then obviously this is not an HTML tag. So that's why we have this negation right here, because this should not be confused with a normal HTML tag. So once we do this, so once we take this kind of example into consideration, and so since we're saying we are not considering this kind of case, it means we're considering a case where we have the B, the R, or whatever which follows, and then we now have this plus, this addition. So we've taken all this, and then once we have this at the end, like here, we're supposing that there's some sort of HTML tag. So in that case, we take this off and we replace it with this empty space. So actually this is not space, we just, in fact, we're just taking it off, because yeah, if we had to replace it with space, we will have something like this, and if we run it, we will have had this line spaces. So basically we're not doing this, we're just replacing it with this kind of null space, so there is no space left right here. So that's basically how we take off this HTML tags. Could have different kind of HTML tags, and note that we'll come back to this. If we have this BR, for example, you see that it's still maintained, because here we're saying don't touch anytime we have BR, or anytime we have B in between this less than and then the greater than sign we have at the end. So Let's maintain this, and we have that. We could also have this with a less than, so it still work fine. So in the case where we have less than, you see that one of the less than signs is left out, which is normal. Anyway, let's take this simply and we'll have that. Now we go to the next. In the next, we tend to take off the punctuation signs. So we're again going to use the TF, the strings, the regex replace. With the regex replace, as we had seen, once we have the regex, or once we identify this, or once we are going through the sentence and we identify a kind of portion which is to be taken off or which is to be replaced, we'll simply do the regex and then we put out the value which is going to replace it. So we'll uncomment the section. Let's check whether we had some punctuations here. Yeah, we didn't have punctuation, so we could add some punctuation signs here, and even some special characters. So let's do this. Run it again. We'll see how we've left from. Okay, there were some punctuation signs here, so that's why we have the spaces now. So like here we have this punctuations which have been taken off with the special characters too. So basically that's it. That's the effect of adding this. So here every time we have a punctuation or a special character, this permits us to take this off and replace it with this. So we could also do this, and we'll find that it's more compact, like it's not replaced by the space. So we have that. Okay, the next is to replace this double spaces with a single space. Now this was actually in the case where, suppose we have we had this like this originally. So in this case we have some double spaces. So when we have double spaces, one that is double spaces should be converted into just a single space. So we could have this, see, it's converted to a single space. Anyway, we have from here already a single space, here double space converted to single space, and then finally we have the lemmatization. So we are seeing that stemming is not the most efficient way of working with sentences or with text, so we prefer to use lemmatization in practice. And to use this, we use the NLTK library. Again, here it's going to be something quite direct. Now we call on the lemmatizer, which comes with nltk.stem. As you could notice, again we have this word stem to say that certain words act like stems to other words, like in the adjective. So if we're considering that we're working with adjectives, see the word better, best, we have a stem good. Then we have a word like, say, words, we have a stem word. Output, we have a stem output. So these are the stems: output, word, and good. So basically that's it. Take this off, and now let's uncomment this portion. So right here we have the lemmatizer, which has been defined already, and now what's left to do is that for each and every word in our input text, we want to lemmatize it. While we run this, find out we have this error because what we get here is the output. So instead of using text, we're supposed to use output, which comes from here. So run this, and now we're told again that this tensor, this eager tensor object, has no attribute split. So tensor, or this output, is actually a tensor, not a string. So suppose we had a string, say out, which is made of different words in the sentence. So suppose we had something like this, or let's just use this. So we have different words in the sentence, and then if we do a print out dot split, which is considering that this out is a string, then here you have a list which is made of the different parts of this string, where each part is a word and all the words make up an element in the list. So basically that's how it works. But now when you have as input a tensor, you have to use TensorFlow's function. So right here we'll replace this, so for word, because basically we're breaking up all these words into and forming this list. So we we could, let's just take this for example. Let's suppose we have this. Let's replace this with this. See, when you run this, you see it breaks each and every word we have here, and once it gets each word, we pass through the lemmatizer, which lemmatizes the word, and then we have a new word. So right here we should replace this with the TensorFlow.strings.split function. So we have that, which takes in the output, or which takes in this input, which is basically this output. Yeah. So with this, we are able to split the different words which are found in the sentence, where that sentence is actually a tensor. So let's run this now and see what we get. We have another error, which comes from the fact that what we're passing in right here is actually a tensor. We could see that because if we do something like this, let's say we print out word. If we print this out, right here you have I, it, should, have, focused on, more, action, and all of that. So basically, should have better. Let's add this up. So we'll do that. Okay. So we could see clearly that these are actually tensors of type string we've been dealing with. We could convert this into a string, but that wouldn't change much. We'll be having strings, but basically the string is going to be made of all these elements, tf, the tensor, and all of that. So let's do this .d type so you could see exactly what I was saying. So you see right here, the string object has no attribute d type. It's just like having this and printing out .d type. See, same result. Now if we take off the string, you wouldn't have this error, but you have the d type string telling you that this is a TensorFlow string. So as we could see clearly, here we actually need a string. So let's take this off. Take this off. We have the string. Let's reprint it again, and you see this. Now let's do this. Let's take from 0 to say 4. So you see how it's going to collect the first 4 elements of each string. Run this, you see. That is, it considered this tf.t as a string, so this isn't very interesting. So we could run. Let's run it back. Let's take this off. We could count from here. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we could start from the 10th element right up to now. To get the next element, you could take from, say, -5. You notice that when you run this, see, it takes this correct. Although we need to take off this values here, this b and then this. So we could take this. We have 12. You see, takes this, and now this last value isn't considered. So this last values, which is the ring, are taken off. So with this, we would go 25 steps. Run it. See, now let's go 26 steps. We have that. Okay. So now we are printing this out. Now let's just basically run the lemmatizer on this. So we have lemmatizer of this. Okay, that should be fine. Now we have this error because we haven't called this correct, the lemmatize. So this should be okay. Okay, so we see that we've successfully converted this and we've lemmatized these values. As you can see, better hasn't changed into good, so we should add the part of speech arguments adjective, and that's fine now. So we've successfully lemmatized this, and then we could take this off, and there we go. For this project, we shall not be using lemmatization, so we just take this off, and we have that. As we had seen in the slides, after pre-processing this sentences, we could go ahead to vectorize it, or to convert the sentences into a form in which our model actually can work on. So to do this, normally you would have to write code to create a vocabulary, to sort this vocabulary in order of number of appearances, to create a word to index dictionary, to create the index to word dictionary, and then based on this dictionary and the vocabulary, generate this one hot output of dimension, batch size, sequence length, and vocabulary size. But then with TensorFlow, we shall see that we could do this with just one step. That's using TensorFlow's easy to use vectorization model. So right here we just have this vectorized layer which we create from text vectorization. We had seen earlier how we imported text vectorization from the pre-processing, which is found in the TensorFlow, the Keras, the layers, the experimental model. So basically that's how we import this text vectorization layer. Now in text vectorization we have the standardize. So the standardize is kind of like taking in the function which we just saw. That's this pre-processed sentences which we saw right here. Basically that's it, which is some sort of customized or custom standardization method or function. And now we have the max tokens. Max tokens basically is the vocab size. We saw on the slides that we had a vocab size of 19. In this case, we're supposing we have a vocab size of 2000, and then a sequence length of 100. So each sentence has a maximum length of 100. If we have an input sentence which has say 50 words, then we are going to pad that input such that it has 100, or it becomes a sentence of a length 100. In case where we have say 150 word sentence, then the 50 last sentence words in this sentence are going to be cut off. So here our sequence length is 100. The next step is to adapt this layer to our training data. So what goes on exactly here is that this vectorized or this text vectorization layer is going to take all our input data, create a vocabulary, create a word to index, create an indexed word, and then from that be capable of generating our output based on our training data set. And it's logical that this layer actually works depending on the training data set. As a different training data set, we have a different vocabulary and hence a different kind of output, and also have different sequence length. So basically this is the most important step where we actually adapt this layer to this training data. But then we are just adapting the inputs and not we are adapting the reviews and not the type of review. So if we have an input like say this one, if we have this kind of input, let's come back to this. Okay, so we have this kind of input where we have this, I think this, anyway, let's scroll down. So we have this input, for example, and its corresponding, okay, ends right here. So we have this input and its corresponding output is a 0, telling us that this is a negative review. So this is the input and then this is the output. For this, our text vectorization layer, we are interested in adapting it with respect to the input and not with respect to the output, or the output and the input. So that is why we're going to create this anonymous lambda function which takes in the input and the output and just outputs the output alone. So now we've modified our training data set to form this training data which is made of just the input, and it's just this input we're going to use to adapt our vectorized layer. So basically that's what we do right here. So from here we could run this and it takes a little while. So now we've created this, we can now create a function vectorizer which takes in the review, this is the review, and then the label, and then returns the vectorized review and the label. So run that, and then we have the train data set, which is equals train data set dot map to this vectorizer, and then we'll repeat the same for the validation data set. Val data set dot map to the vectorizer. So that's it. So what happens here is each of these values, that the reviews and the labels, are passed, and then the vectorized layer which we had defined before actually takes care of converting these reviews or putting them in a form which can be consumed by a model, and then also outputting this label. So let's run this and see what we have from here. Now after running, let's run for review label in, say, the train dataset dot take. Let's just take one of that. We're gonna print out the review and its corresponding label. So print out the corresponding label. Okay, so when we look at this, we have obviously 8 different values since our batch size is that of 8. So we have this values. We recall that initially we had sentences, but now we have this vectors which now form this matrix we have of dimension, batch size by sequence length. So the kind of matrix we have in here is one in which instead of having this one hot notation, we have a start with actually the value 0. Next, for the next value, we have this value 1, for example. Let's instead use this example since it's going to be clearer. So as we said here, when we have the start, we have this value 0. The there gives us this value 4. So instead of putting this one hot notation, we have the value 4. The actors, we have the value 6, so on and so forth. So instead of having, as we had seen, the batch size by sequence length by vocabulary size, we have just batch size by sequence length, since each of these, that's each of the words, are represented by just one letter or one figure which represents that word's position in the vocabulary. So if we choose, for example, this in the vocabulary, in is position position 7. Okay, so since in is position 7, instead of having this one hot notation, we just have a value 7. Hence that matrix formed is of dimension, batch size by sequence length. Now we're going to see how to convert that matrix into one of these 3 dimensions. So we're going to have batch size by sequence length by vocabulary size. Now since we are going to convert each of these figures into a one hot vector, so if we have, like in the case of in, where we have 7, we're going to convert into one hot notation or into one hot vector, such that if we have 7, we have a vector made of all zeros, but at the 7th position we have a 1. So to do that, as we had seen, we're just gonna use TensorFlow's one hot function, which comes already made with the TensorFlow. Now before continuing, note that here most times we don't have any padding, since the sequence length of 100 is quite small for the kind of data set we're having. If we choose a sequence length of, say, 1000, we would have had many instances where we had to do some padding. And also we could look at the vocabulary which we are dealing with. Say, for example, with the vectorized layer, we could say vectorized layer dot get the vocabulary. So with this, we could get the whole vocabulary. So we could see here that this is the 0th, this is the first, second, third, and all of that. So any point where you have the second means the input word was a de. So this is a de. The seed position, if you have 2, 3, 4, 5, 6, there was a 2. So here was a 2, it's a de, and you could always get all the rest of the values, all the rest of the I think 1000 values. No, it should be 2000 values, since our vocabulary size is 2000. So if we could calculate the length of this, so we just do length of this. The length of this is 2000, as you can see. So that's our vocabulary we have, and the rest which do not fall into vocabulary are considered to be unknown. So if you have any word that's not in this vocabulary, it's unknown, hence it's going to take the value 1. So many times when you have this value 1, it's simply because the word did not occur so many times such that it did not actually fall in our vocabulary. But note that you could always increase this vocabulary size and sequence length depending on the kind of problem you have. But here we just decided to work with this. So that said, let's modify our code. Come back to the vectorized layer. We have tf.one hot. So basically that's all we need to do. tf.one hot, and then we'll specify the depth. So we have this depth, which is equals the max features or the vocabulary size in this case. So just basically our vocab size. Now let's explain that. We could take this off. So we could, anyway, let's do it right here. So suppose we have this input. So suppose we have this input A, for example. So we have A, which is say 2, 4, 6, and then this is A is equals tf the constant of A. So this is our tensor. Now let's print out A. So if we print out A, we have this, basically that's normal. And then let's go ahead to print out tf.one hot of A with a depth of say 2. Okay, so we run this. Since our depth is 2, we have, and we had this 3 different values. For the first value, that's this 2, we have this first vector, and our depth is 2. That's why we just have 2 positions for the 0 and the first. Now 2 doesn't fall in this, so that's why we have 0, 0, 0, 0, 0, 0. This other 0, 0 is for the 4, and this 0, 0 is for the 6. Now let's increase this depth to take, for example, 4. You see that now this 2 falls in because this is 0 position, first position, second position, and this 2 falls, so that's okay. Now for this 4, it doesn't fall because it's the third position and that's not found there. So we could increase this to 6, 7, and once we do this, we have a 1 hot representation of this input vectors. So this 2 is this 4 is 0, 1, 2, 3, 4. The 6 is 0, 1, 2, 3, 4, 5, 6. So that's okay. Now if you keep on increasing this, it won't actually change much because this value fall in that range. So let's just maintain this at 7. So the whole idea here is to actually have this depth such that it matches with the kind of inputs we shall have, because our inputs will obviously vary from 0 to 2000. So we just select this our depth to have this plus 1. So that's it. Okay, so once we have this, we could run it again, and then right here we could rerun our training set and then reprint it. We have this error because the input here is a vector of figures, or better still of numbers, since we had already passed the vectorized layer on each review. So we to have the correct answer here, we just have to go back and then rerun this. So we should rerun this and that should be fine. So we're just gonna recreate this vectorized layer, or readapt the vectorized layer. We also have this other error because of the form of the trained data set. So basically let's go back and rerun the whole program. So let's run this, run it again. Could comment this path. Oh, let's just run all this. So we run all this, run it, and then run this path. Finally we run this. So we should run that and see what we have after getting, or after transforming each element of the train and the validation set. Okay, so after running this, now everything works fine. We have our training set. Notice that where we had just one number like this, or we had just, let's take this one for example, here we should have had the number 1. Instead of having the number 1, we have this 1 hot representation of 1, where we put at the position 1 the value 1 and the remaining values are zeros. Now note that this is the unknown as we had seen before, so unknown takes the first position. So basically with 1 hot, or we've converted the input sentences into this tensor, which is of dimension 8, that's the batch size, by 100, that's sequence length, by 2000, which is the vocabulary size. And then lastly, to work more efficiently with our data, we can have the train dataset, which is equal to train dataset dot cache dot prefetch with buffer size, which is auto-tune. We'll repeat this for the validation. Now we could go ahead to import that auto-tune. So we have this from TensorFlow data experimental import auto-tune. So that's fine. Now we go ahead to run this, print out. I'll just have train data set. Okay, so we see clearly that this is our this is our train data set, which is ready to be consumed by a model and ready to be used by a model to train it, such that when it says new input reviews, you could say whether it's a positive review or not.